The white hole hypothesis. The white hole hypothesis is an exciting and imaginative idea in physics. A white hole is thought to be the opposite of a black hole. While black holes pull in everything that gets too close, white holes would do the reverse. They would push out matter and energy, and nothing could go inside. Black holes are well studied and supported by evidence, but white holes are purely theoretical. If they exist, they might teach us more about how the universe works, including the nature of space, time, and even the origins of everything around us. Including the nature of space, time, and even the origins of everything around us. What is a white hole? A white hole comes from the same science that gave us black holes, Einstein's general theory of relativity. A black hole is formed when a massive star collapses under its own gravity, creating a region where nothing, not even light, can escape. A white hole would be the reverse. It's a region that constantly throws out matter and energy and doesn't allow anything to enter. Imagine a black hole as a one-way trap. Everything that crosses its boundary, called the event horizon, is pulled inward and lost forever. A white hole, on the other hand, would act like a one-way fountain. Matter and energy would shoot outward and nothing could go in. This idea is very different from how we usually think gravity works. Where did this idea come from? The idea of white holes comes from the same math that describes black holes. In 1916, Karl Schwarzschild solved Einstein's equations of general relativity and discovered how gravity behaves around a spherical object like a star. This math predicted black holes, and it also hinted at the possibility of white holes. White holes use the same spacetime geometry as black holes, but with time running backward. If a black hole shows how matter collapses inward, a white hole might show how matter explodes outward. This idea fits with a concept in physics called time symmetry, which says that the laws of nature should work the same whether time moves forward or backward. However, while black holes have been observed indirectly, white holes remain an open question. They may exist only in the math, not in the real universe. Could white holes be linked to black holes? One of the most fascinating parts of the white hole hypothesis is its possible connection to black holes. Some scientists think white holes and black holes might be two sides of the same thing, linked in ways we don't fully understand. Wormholes and spacetime shortcuts. A popular theory is that black holes and white holes could be connected by a wormhole. A wormhole, also called an Einstein-Rosen bridge, is a theoretical tunnel through spacetime. In this idea, matter falling into a black hole might travel through the wormhole and come out of a white hole, possibly in another part of the universe, or even in a different universe altogether. However, wormholes are highly speculative, and keeping them stable would require strange materials that we've never observed. White holes as the end of black holes. Another theory suggests that white holes might form when black holes die. Black holes slowly lose mass over time by emitting Hawking radiation, a process discovered by Stephen Hawking. As a black hole evaporates completely, it could transition into a white hole, releasing all the information and matter it absorbed. This idea could help solve the information paradox, a big question in physics about whether information is truly lost in black holes. The Big Bang is a white hole. Some physicists think the Big Bang, which started our universe, might have been a white hole event. In this view, the universe could have been born from a white hole ejecting all the matter and energy that now make up stars, planets, and galaxies. Matter and energy that now make up stars, planets, and galaxies. If true, this raises even more questions. Could there be other universes, each created by its own white hole? This is a mind-boggling idea, but it remains purely speculative. Challenges to the white hole hypothesis. While the idea of white holes is fascinating, there are some big problems with it. No observational evidence. Unlike black holes, which have been detected by their effects on nearby stars and the light they emit as they pull in matter, no one has ever seen a white hole. Their existence is still just an idea based on math. Stability issues. White holes seem unstable in most scientific models. If they constantly eject matter and energy, they would likely collapse quickly or turn into black holes if they interacted with surrounding material. Causality problems. White holes create strange situations where effects seem to happen without causes. For example, they eject matter without any clear explanation of where that matter came from. This clashes with how we understand cause and effect in physics. Why does the white hole hypothesis matter? Even if white holes don't exist, studying them is still valuable. They challenge scientists to think about extreme conditions in the universe and the limits of what we know. Exploring the white hole hypothesis helps us better understand space-time, the nature of gravity, and how time itself works. White holes are also connected to some of the biggest questions in science, like how to combine quantum mechanics, the physics of very small things, with general relativity, the physics of very large things. If white holes are linked to black holes, studying them might offer clues about quantum gravity, the missing piece that could unify these two areas of physics. Finally, the idea of white holes sparks our imagination. Could the universe have been born from a white hole? Are there other universes connected to ours through wormholes? These are exciting questions that push the boundaries of what we think is possible and inspire us to learn more about the cosmos. The time dilation paradox. The time dilation paradox is a fascinating mystery that comes from the way time behaves near a black hole. It's based on a strange idea. Time doesn't flow the same way for everyone. When someone falls into a black hole, their experience of time is very different from what an outside observer sees. To the person falling in, time feels normal. But to someone watching from far away, the falling person seems to slow down, stop, and never fully disappear. This odd difference challenges how we think about time and reality. What is time dilation? Time dilation means that time can pass at different rates depending on where you are or how fast you're moving. According to Einstein's theory of general relativity, massive objects like black holes bend the fabric of space and time. This bending slows time down near the massive object. The stronger the gravity, the slower time moves. Black holes take this effect to the extreme. They have such strong gravity that time near them almost stops compared to time far away. At the edge of a black hole, called the event horizon, this effect is so intense that time seems to freeze from the perspective of a distant observer. The paradox. Two perspectives on time. The time dilation paradox happens because two observers, one falling into the black hole and one watching from far away, experience time differently. The falling observer, for the person falling into the black hole, nothing seems unusual. Time feels normal, and they pass through the event horizon without noticing anything strange. Eventually, they reach the center of the black hole, called the singularity, where gravity is infinitely strong. The outside observer. To someone watching from far away, things look very different. As the falling person approaches the event horizon, they seem to slow down more and more. From this perspective, the falling person never actually crosses the event horizon. Instead, their image stretches, becomes dimmer, and eventually fades away due to the black hole's gravity. This creates a paradox. From the falling person's view, they cross the event horizon and reach the singularity. From the outside observer's view, the falling person never fully crosses the event horizon. So who is right? According to relativity, both perspectives are correct in their own way. Time and space behave differently depending on where you are, and both experiences can be true at the same time. Why does this matter? The time dilation paradox is important because it reveals the strange nature of time and challenges our everyday ideas about it. Here's why it matters. Time is not absolute. We usually think of time as something that moves at the same speed for everyone, everywhere. The paradox shows that this isn't true. Time is flexible and depends on where you are and how gravity affects you. Black holes and growth. If objects never seem to cross the event horizon from an outside perspective, how does a black hole grow? Scientists know that black holes do grow, but this paradox raises questions about how matter and energy actually interact with black holes. The nature of reality. The paradox highlights that reality isn't the same for everyone. Two people can experience the same event in completely different ways, and both can be right. This idea is strange but fundamental to Einstein's theory of relativity. It's something we measure in everyday life. For example, GPS satellites orbiting Earth experience weaker gravity than we do on the surface, so their clocks run slightly faster. Scientists must adjust for this difference to make GPS systems accurate. Possible explanations for the paradox. Scientists have proposed several ideas to explain the time dilation paradox. Here are some of the most interesting ones. Relative observers. The simplest explanation is that both the falling person and the outside observer are correct in their own frames of reference. Time and space behave differently depending on where you are, and these differences don't contradict each other. They just reflect the strange nature of space-time. Black hole growth. While the outside observer sees the falling object slow down, black holes are observed to grow over time. This suggests that even if the process isn't directly visible, the energy and mass of the falling object are still added to the black hole. Hawking radiation complicates the picture. This radiation slowly causes black holes to lose mass and eventually evaporate. How this fits with the idea of objects freezing at the event horizon is an ongoing area of research. Quantum mechanics. Some scientists think that quantum mechanics might resolve the paradox. For example, quantum effects could allow information about the falling object to be stored on the event horizon, even as the object itself continues into the black hole. The holographic principle. This idea suggests that all the information about the falling object is encoded on the event horizon in 2 dimensions. From the outside, the object is smeared across the horizon, while from the falling observer's perspective, they continue into the black hole. This duality could reconcile both views. What we learn from the paradox. The time dilation. Paradox teaches us a lot about the universe. Time and space are interconnected. Time and space are interconnected. Time isn't a simple, constant flow. It's deeply linked to space and gravity. Massive objects like black holes stretch and warp time, creating strange effects that challenge our intuition. Perspective matters. In relativity, what one observer sees can be completely different from what another sees, and both can be true. This forces us to think about reality in new ways. Black holes and beyond. The paradox helps us explore deeper questions about black holes, time, and gravity. Understanding these extreme environments could lead to new breakthroughs in physics. Everyday impacts. Time dilation isn't just a theoretical concept. It's something we deal with in technology, like GPS systems. Studying extreme cases like black holes helps us better understand these effects. The time dilation paradox is more than a strange curiosity. It's a window into the weird and wonderful nature of time, gravity, and the universe. By exploring this paradox, we not only learn about black holes, but also uncover the surprising flexibility of reality itself. The black hole entropy paradox. The black hole entropy paradox is a big puzzle in science that makes us rethink some of the basic rules of how the universe works. It's about black holes, mysterious objects in space where gravity is so strong that nothing can escape, not even light. The paradox revolves around an idea called entropy, which measures the disorder or complexity of a system. What's strange about black holes is that their entropy is not like most things we see in the universe. For regular objects, entropy is linked to their volume, how much space they take up. But for black holes, entropy is tied to their surface area, specifically the area of their event horizon, the invisible boundary where nothing can escape. This unusual fact doesn't match our usual understanding of physics, creating a paradox. What is entropy? To understand the paradox, let's first talk about entropy. In physics, entropy is a way to measure how much disorder or randomness exists in a system. For example, a neat stack of books has low entropy because there's only one way to arrange it neatly. A messy pile of books has high entropy because there are many ways to create the mess. In most systems, the entropy grows as the system gets bigger. If you have more particles or more space, there are more possible ways to arrange everything. So entropy is usually proportional to volume. Why are black holes different? Black holes don't follow the usual rule. In the 1970s, physicist Jacob Bekenstein suggested that black holes have entropy. Later, Stephen Hawking showed that black holes aren't completely black. They emit energy, now called Hawking radiation, and slowly lose mass over time. These discoveries led to a surprising conclusion. A black hole's entropy depends only on the area of its event horizon, not its volume. This formula shows that as a black hole's surface area grows, its entropy increases, even though we'd normally expect entropy to depend on volume. This creates the black hole entropy paradox. Why does this matter? The black hole entropy paradox challenges some of the most important ideas in physics. Here's why it's so important. Entropy in thermodynamics. Entropy is a key concept in thermodynamics, the study of heat and energy. Black holes behaving differently suggests that the laws of thermodynamics might not work the same way in extreme conditions. Quantum mechanics and gravity. Black holes are governed by general relativity, which explains gravity, but their entropy hints at hidden quantum processes. Combining these two theories, quantum mechanics and general relativity, is one of the biggest challenges in science. Nature of information. The fact that black hole entropy depends on surface area suggests that information about what's inside the black hole is somehow stored on its boundary. This idea is so unusual that it could change how we think about space, time, and the nature of reality limits of our knowledge. The paradox shows that the universe might not work the way we think, especially in extreme places like black holes. It hints that we're missing some deeper understanding of physics. Ideas to solve the paradox. Scientists have come up with several ideas to try to solve the black hole entropy paradox. While none of these are proven, they offer fascinating possibilities. The holographic principle. This idea says that all the information about a region of space can be encoded on its surface. For black holes, this means the information inside might actually be stored on the event horizon. The principle suggests that the entire universe might work this way, with three-dimensional objects being like projections of two-dimensional information. String theory and quantum gravity. String theory, a possible theory of quantum gravity, proposes that black holes are made of tiny vibrating strings. The way these strings arrange themselves might explain why black hole entropy depends on surface area. This theory also supports the idea that information is stored at the event horizon. Microscopic states of black holes. Some scientists are trying to calculate the tiny quantum states inside a black hole, treating it as a thermodynamic system. If they can count these states, they might show how entropy is linked to the event horizon. New laws of physics. The paradox might mean that we need new laws of physics. These new rules could explain how entropy, quantum mechanics, and gravity interact in black holes, leading to a unified theory. What the paradox teaches us, the black hole entropy paradox, is not just about black holes. It's about how the universe works at the deepest level. Here's what it tells us. Information and reality. The paradox suggests that information might not be tied to the volume of space, but instead to its surface. This changes how we think about storing and transmitting information in the universe. The need for a unified theory. To fully understand black holes, we need a theory that combines quantum mechanics and gravity. The paradox is a clue that these two frameworks are incomplete on their own. The universe is a hologram. The idea that black hole entropy depends on surface area supports the concept of a holographic universe. This means the three-dimensional world we experience might be a projection of two-dimensional information. Extreme conditions test physics. Black holes are unique places where normal physics breaks down. Studying them gives us a chance to discover new laws that govern the universe in extreme conditions. Why the paradox remains unsolved even after decades of research. The black hole entropy paradox is still a mystery. It challenges our understanding of basic ideas like entropy, information, and space. Our understanding of basic ideas like entropy, information, and space. Solving this puzzle could unlock new insights about the universe and lead to breakthroughs in physics. Black holes, once thought to be simple and mysterious objects, are now seen as key to understanding the nature of reality. They are not just places in space, they are windows into the most fundamental questions about how the universe works. The singularity paradox is one of the biggest mysteries in science. It focuses on something called a singularity, a strange point at the center of a black hole where the rules of physics break down. At this point, gravity becomes infinite, and space and time seem to stop making sense. Scientists struggle to explain how such a state can exist, making this one of the toughest challenges in understanding the universe. What is a singularity? A singularity forms when a massive star dies. Stars produce energy by burning fuel in their cores, but when the fuel runs out, the star collapses under its own gravity. If the star is big enough, this collapse creates a black hole. Inside the black hole, all the star's matter gets squished into an incredibly tiny point with infinite density and zero volume. This is the singularity. The pull of gravity at the singularity is so strong that not even light can escape, which is why black holes are completely dark. Here's the problem. Infinite density and zero volume don't make sense in physics. They're not things we can measure or observe in the real world. These infinities suggest that our current understanding of physics is incomplete. The clash between two theories, the singularity paradox, shows a conflict between the two main theories of physics. General relativity. This is Einstein's theory of gravity, which explains how massive objects like stars and black holes affect space and time. General relativity predicts that singularities must exist as the result of extreme gravity. According to this theory, space and time themselves are crushed out of existence at the singularity. Quantum mechanics. This is the theory that describes the behavior of very small things, like atoms and particles. It relies on probabilities and patterns, but it can't handle the infinities found in a singularity. Quantum mechanics breaks down when faced with infinite density and zero volume. Because singularities involve both extreme gravity and tiny scales, they expose the limits of these two theories. Neither can fully explain what happens at a singularity, making it a point of no return for our understanding. Why does the singularity paradox matter? This paradox isn't just about black holes. It challenges our entire understanding of the universe. If singularities truly exist, they break the idea that the universe follows consistent physical laws. How can something exist that defies the very rules that created it? On the other hand, if singularities don't exist, what's really at the center of a black hole? The singularity paradox also relates to the Big Bang, the event that created the universe. The Big Bang theory suggests that the universe started as a state similar to a singularity, an incredibly dense and tiny point. By understanding black hole singularities, we might uncover clues about how the universe began. Ideas to solve the singularity paradox. Scientists have proposed several ideas to resolve this paradox. Each one involves going beyond the current theories of physics. Quantum gravity. Many believe that a new theory combining general relativity and quantum mechanics, called quantum gravity, will solve the paradox. This theory could reveal that singularities aren't truly infinite, but represent a state we don't yet understand. String theory. String theory is a leading candidate for quantum gravity. It suggests that the basic building blocks of the universe are tiny vibrating strings instead of point-like particles. These strings have a finite size which could prevent the infinities of singularities and create a smallest possible scale for matter and energy. Loop quantum gravity. Another idea is loop quantum gravity, which proposes that space and time are made of tiny finite pieces. If space-time isn't continuous, it could prevent singularities by creating a quantum bounce. Instead of collapsing into a singularity, matter might reach a minimum size and then expand again. Cosmic censorship hypothesis. Some scientists believe that singularities are always hidden behind the event horizon of a black hole, where they can affect the outside universe. This idea, called the cosmic censorship hypothesis, suggests that singularities are more of a mathematical artifact can affect the outside universe. This idea, called the cosmic censorship hypothesis, suggests that singularities are more of a mathematical artifact than a real physical entity. Exotic states of matter. Other theories suggest that singularities might not exist at all. Instead, the extreme conditions inside a black hole could create exotic forms of matter. This matter might form a dense core that avoids the infinities predicted by general relativity. These cores could offer a more realistic description of what's inside a black hole. What we can learn from the singularity paradox. The singularity paradox is more than just a puzzle. It's a chance to learn about the unknown. It reminds us that our current understanding of physics is limited and that we need new ideas to learn about the unknown. It reminds us that our current understanding of physics is limited and that we need new ideas to explain the universe. The paradox also shows how different areas of science are connected. General relativity works well for big things like stars and galaxies, while quantum mechanics explains small things like particles. Singularities sit at the boundary of these two theories, forcing us to combine them into a unified theory. Finally, the paradox raises big questions about reality itself. What happens to space and time at a singularity? Are there limits to what we can know about the universe? By studying these questions, we can move closer to understanding the deepest mysteries of existence. Hawking radiation and black hole evaporation. In the 1970s, the famous scientist Stephen Hawking made a groundbreaking discovery about black holes. He showed that black holes are not completely black. Instead, they emit a faint glow of energy called Hawking radiation. This discovery changed how we think about black holes, quantum mechanics, and even the nature of the universe. But it also raised a big question. What happens to the information about everything that falls into a black hole when the black hole eventually disappears? What is Hawking radiation? To understand Hawking radiation, we first need to know what a black hole is. A black hole is a region in space where gravity is so strong that nothing, not even light, can escape. This is why black holes are black. According to quantum mechanics, tiny particle pairs are constantly appearing and disappearing everywhere in space. These pairs are made up of a particle and its opposite, called an antiparticle. Normally, these pairs quickly cancel each other out and vanish. But near the edge of a black hole, something different happens. The intense gravity can pull the pair apart before they can cancel out. One particle falls into the black hole, while the other escapes into space as Hawking radiation. This escaping particle takes energy away from the black hole. What happens to the black hole? As the black hole loses energy through Hawking radiation, it starts to shrink. Over time, this process continues until the black hole gets smaller and smaller. Eventually, it disappears entirely. This process is called black hole evaporation. For big black holes, this process is extremely slow. It would take longer than the age of the universe for a large black hole to fully evaporate. But for smaller black holes, evaporation happens much faster. When a small black hole nears the end of its life, it emits a burst of energy and disappears. The problem: where does the information go? Here's the big mystery. When a black hole evaporates, what happens to the information about everything that fell into it? Information means the details about the objects, what they were made of, their shape, their energy, and so on. Quantum mechanics, one of the most important theories in physics, says that information can never be destroyed. Even if something changes form, like ice melting into water, the information about it still exists. But Hawking radiation seems to carry no information about what was inside the black hole. If the black hole disappears completely, it looks like the information is lost forever. This creates a conflict between two major ideas in physics. Quantum mechanics, which says information is always preserved. General relativity, which explains black holes and doesn't require information to be preserved. This conflict is known as the information paradox, and it's one of the biggest puzzles in modern science. Possible solutions to the information paradox. Physicists have suggested several ideas to solve the paradox, but none have been fully proven yet. Here are some of the main possibilities. Hawking radiation contains information. Some scientists think that Hawking radiation might not be completely random. Instead, it might carry tiny hints about the black hole's contents. Over time, as the black hole evaporates, all the information could slowly leak out. This idea fits with quantum mechanics, but proving it is extremely difficult. The holographic principle, another idea, is that all the information about what falls into a black hole is stored on its surface, the event horizon. In this view, the event horizon acts like a 2D storage system for 3D information. The black hole's interior would then be like a hologram of this stored information. This ensures that the information isn't lost, it's just stored in a way we don't fully understand. Black hole remnants. Some researchers believe that black holes might leave behind tiny, stable objects called remnants after they evaporate. These remnants could hold all the information that fell into the black hole. However, this raises new questions about what these remnants are and how they behave. New theories of physics. Questions about what these remnants are and how they behave. New theories of physics. Some scientists think the paradox might mean that our current understanding of physics is incomplete. A new theory that combines quantum mechanics and general relativity, called quantum gravity, might explain how information is preserved during black hole evaporation. Information escapes to another universe. One speculative idea is that black holes might act as gateways to other universes. In this case, the information wouldn't be lost. It would just be inaccessible to us. Why is this important? The discovery of Hawking radiation showed that black holes are not as simple as we once thought. They are not just places where things disappear forever. Instead, they are complex systems that connect the rules of quantum mechanics and general relativity. But the information paradox is more than just a puzzle about black holes. It's a sign that our two best theories of physics, quantum mechanics, and general relativity, don't fully agree. Solving this problem could lead to a new understanding of the universe, helping us create a theory of quantum gravity that explains both the very small and the very large. The ongoing mystery physicists are still working to understand Hawking radiation and the information paradox. No one knows for sure what happens to information when a black hole evaporates, but the search for answers has already expanded our understanding of black holes, quantum mechanics, and the nature of reality itself. While the mystery remains unsolved, it continues to inspire new ideas and discoveries, pushing the boundaries of human knowledge. The singularity paradox. The no-hair theorem is a simple but surprising idea about black holes. It says that black holes can be completely described by just three things. Mass, how much stuff the black hole has. Charge, its electric charge, though most black holes are neutral. Spin, how fast it's rotating. This means that black holes don't have any extra details or features. No matter what fell into the black hole, stars, dust, or even a spaceship, all that complexity is erased. The black hole only keeps track of its mass, charge, and spin. This simplicity has made the no-hair theorem an important idea in understanding black holes, but it also creates big questions about how information works in the universe. What does the no-hair theorem say? The term no-hair is a metaphor. Think of hair as any extra details or unique features about a black hole. The no-hair theorem says that black holes don't have this kind of hair. All black holes with the same mass, charge, and spin are identical even if they were formed in completely different ways. For example, if one black hole forms from a collapsing star and another forms from a collection of gas, as long as their mass, charge, and spin are the same, they will look exactly alike. This simplicity makes black holes easier to describe, but it also raises big questions about what happens to the lost details of the matter that fell into the black hole. Why is the no-hair theorem important? The no-hair theorem is more than just a rule about black holes. It connects to one of the biggest puzzles in science, the information paradox. Here's why. According to quantum mechanics, information is never destroyed. This means that the details about what falls into a black hole, its chemical makeup, structure, and history, should somehow still exist. But the no-hair theorem says that black holes erase everything except for mass, charge, and spin. If this is true, it seems that information is lost forever. This creates a conflict between the no-hair theorem, based on general relativity, and quantum mechanics. Resolving this conflict is key to understanding how the universe works. Evidence for the no-hair theorem scientists have tested the no-hair theorem by observing black holes and studying their behavior. One way they do this is by looking at gravitational waves, ripples in spacetime caused by massive events like black hole collisions. In 2015, the LIGO experiment detected gravitational waves for the first time. These waves came from two black holes merging. The properties of the merged black hole matched the predictions of the no-hair theorem. Since then, other detections have also supported the theorem, showing that black holes behave as expected based on their mass, charge, and spin. However, while these observations confirm the simplicity of black holes, they don't explain what happens to the information that seems to disappear. Challenges and controversies. The no-hair theorem is widely accepted, but it's not without its problems. Black holes in isolation. The theorem assumes black holes exist in a vacuum, away from other matter. In reality, most black holes interact with their surroundings, which could affect their properties. Soft hair. Some scientists suggest that black holes might have tiny subtle features called soft hair that store information in ways we don't yet understand. This idea challenges the simplicity of the no-hair theorem, but could help solve the information paradox. Quantum gravity. The no-hair theorem comes from general relativity, which doesn't account for quantum mechanics. To fully understand black holes, scientists need a theory of quantum gravity that combines these two frameworks. This might reveal that black holes are more complex than the theorem suggests. Why does the no-hair theorem matter? The no-hair theorem raises deep questions about the universe. If black holes erase information, does this mean there are places where the rules of quantum mechanics break down? Can information truly be lost, or is it stored in a way we haven't discovered yet? What does this mean for our understanding of cause and effect? Beyond these philosophical questions, the theorem is also practical. If all black holes with the same mass, charge, and spin are identical, it makes them easier to describe and predict. This helps scientists study black holes and understand how they form and evolve. What can we learn from the no-hair theorem? The no-hair theorem shows the balance between simplicity and complexity in nature. It simplifies black holes to just three properties, making them easier to study. But it also forces us to confront difficult questions about information and quantum mechanics. This theorem also reminds us of the limits of our knowledge. It works well within general relativity, but it doesn't explain what happens at the smallest quantum levels. As scientists continue to explore these mysteries, the no-hair theorem will remain a key part of our efforts to understand black holes and the universe itself. Firewall paradox. The firewall paradox is a big puzzle in science that has to do with black holes. It suggests something very strange. Instead of being smooth and calm at the edge of a black hole, called the event horizon, there might be a wall of intense energy called a firewall. If this is true, anything falling into the black hole would burn up at the event horizon. This idea creates a major conflict in physics. Einstein's general relativity says that falling into a black hole should feel smooth and uneventful at first, with nothing unusual happening at the event horizon. But the firewall hypothesis says the opposite. It predicts a violent, fiery barrier. These two ideas can't both be true, so scientists are left with a paradox. How do black holes work? To understand the firewall paradox, let's first look at how black holes are supposed to work according to Einstein's theory of general relativity. A black hole is a place in space where gravity is so strong that nothing, not even light, can escape it. The event horizon is the boundary of the black hole, the point where anything that crosses it is trapped forever. Einstein's theory predicts that falling through the event horizon would feel completely normal. This is because of a principle called the equivalence principle, which says that the laws of physics should feel the same for all observers, no matter where they are or how fast they're moving. According to this idea, crossing the event horizon should not involve any sudden, dramatic effects. However, when we consider quantum mechanics, the rules that govern tiny particles, things get more complicated. What is a firewall? The firewall hypothesis says that instead of a smooth event horizon, there's a blazing wall of energy around the black hole. This energy comes from a breakdown in the quantum connections called entanglement between particles inside the black hole. This energy comes from a breakdown in the quantum connections called entanglement between particles inside the black hole and those in the radiation it emits, known as Hawking radiation. Hawking radiation happens because of quantum effects near the event horizon. Over time, this radiation causes the black hole to lose mass and eventually disappear. To follow the rules of quantum mechanics, information about everything that falls into the black hole must somehow escape in this radiation. But for this to happen, the quantum entanglement between particles must break, releasing enormous energy and creating the firewall. If firewalls exist, they would destroy anything that tries to pass through the event horizon. This directly challenges the smooth and calm event horizon predicted by general relativity, creating a serious conflict between these two powerful theories. Why does this matter? The firewall paradox matters because it points to a big problem with our understanding of the universe. Quantum mechanics and general relativity are two of the most successful scientific theories ever developed, but the paradox shows that they don't agree when it comes to black holes. This suggests that at least one of these theories is incomplete, or that we're missing a deeper explanation that can combine them. The paradox also challenges our understanding of space-time, the fabric of the universe. If firewalls exist, it means space-time isn't smooth and continuous near a black hole, as general relativity suggests. Instead, it would break down under extreme conditions, raising questions about how the universe works at its most fundamental level. Ideas to solve the paradox. Scientists have come up with several ideas to resolve the firewall paradox, but none of them have been proven yet. Here are the main proposals. Firewalls are real. Some physicists believe that firewalls must exist to preserve the rules of quantum mechanics. If this is true, it means we need to rethink general relativity and accept that the event horizon isn't smooth. Information escapes without firewalls. Others argue that black holes preserve information in the Hawking radiation without the need for firewalls. This idea would require new ways to explain how information is encoded in the radiation while keeping the event horizon smooth. Complementarity. This idea says that the conflict arises because we're looking at black holes the wrong way. From the outside, it appears that information escapes in Hawking radiation. From the perspective of someone falling into the black hole, the event horizon seems smooth and they experience no firewalls. Both views are correct, but they can't be observed at the same time. This explanation comes from string theory and tries to combine quantum mechanics and general relativity. New physics. Some scientists think the paradox shows that we need a new theory that combines quantum mechanics and general relativity, often called quantum gravity. Such a theory could resolve the paradox and give us a deeper understanding of black holes. What does the firewall paradox teach us? The firewall paradox is more than just a problem about black holes. It challenges how we think about the universe at its most basic level. It forces scientists to confront the possibility that even our best theories are incomplete. This paradox also shows that black holes are not just exotic objects in space. They are windows into some of the biggest mysteries of physics. By studying black holes and their paradoxes, we're not only learning about gravity and quantum mechanics, we're also exploring questions about the nature of reality itself. In the end, the firewall paradox reminds us of the limits of human knowledge and the complexity of the cosmos. It's a humbling example of how much we still have to learn about the universe. Solving this mystery could lead to breakthroughs in our understanding of space-time, gravity, and the quantum world, taking us closer to a complete picture of how the universe works. The information paradox is a big mystery in science. It's about what happens to information when something falls into a black hole. A black hole is a strange place in space with gravity so strong that nothing can escape it, not even light. This means we can't see what's inside a black hole or know what's happening there. Here's where the problem begins. When something falls into a black hole, it seems like all the information about it is gone forever. But one of the basic rules of physics, called quantum mechanics, says that information can never be completely destroyed. So how can this be true if black holes seem to make information disappear? This is the information paradox, and it has puzzled scientists for a long time. Why is this important? The information paradox isn't just about black holes. It's about understanding how the universe works. Scientists have two big theories to explain nature. Quantum mechanics helps us understand the tiniest things like particles and atoms. It says that information is always preserved even if things change form. General relativity explains how gravity works and how big objects like stars and black holes behave. It describes black holes perfectly, but doesn't say anything about preserving information. Both of these theories work very well, but the paradox shows they don't agree with each other when it comes to black holes. This is a huge problem because these two theories are the foundation of modern physics. To solve the paradox, scientists need to figure out how these theories can work together. This could lead to a new theory that explains everything in the universe, often called quantum gravity. How do black holes create this problem? To understand the paradox, let's look at what happens around a black hole. A black hole has a boundary called the event horizon. Once something crosses this boundary, it's trapped forever and can't escape. Even light can't get out, which is why black holes are black. In the 1970s, a famous scientist named Stephen Hawking discovered something surprising. Black holes aren't completely black. They slowly give off energy called Hawking radiation because of tiny quantum effects near the event horizon. Over time, this radiation makes the black hole shrink and eventually disappear. But there's a problem. Hawking radiation doesn't carry any information about what fell into the black hole shrink and eventually disappear. Hawking radiation doesn't carry any information about what fell into the black hole. If the black hole completely evaporates, it seems like all the information about what went inside is lost forever. Quantum mechanics says this can't happen. Information can't just vanish. So what's going on? This is the heart of the information paradox. Why does losing information matter? Losing information might not sound like a big deal, but it's actually a huge problem for physics. If black holes destroy information, it would mean that quantum mechanics, a theory that has been proven in countless experiments, is wrong or incomplete. It would also mean that we don't fully understand how the universe works. The paradox also raises big philosophical questions. If information can disappear forever, how can we understand the past? Can we trust cause and effect? If the universe can lose information, does that mean there are limits to what we can ever know? These questions go beyond science and challenge how we think about reality itself. Ideas for solving the paradox. Scientists have come up with several ideas to solve the information paradox, but none of them have been fully proven. Here are some of the most interesting ones. The holographic principle. This idea suggests that all the information about what falls into a black hole is stored on its surface, the event horizon. It's like the information is written on the black hole's skin, instead of being lost inside. In this view, the inside of the black hole is just a 3D projection of the information on its surface. If this is true, the information isn't really gone, it's just stored in a way we don't understand yet. Hawking radiation carries information. Some scientists believe that Hawking radiation might not be completely random. Instead, they think it could carry tiny pieces of information about what fell into the black hole. Over time, as the black hole shrinks, all the information might slowly leak out through this radiation. If this is true, it would fit with the rules of quantum mechanics. Black hole remnants. Another idea is that black holes don't disappear completely. When they evaporate, they might leave behind small, stable objects called remnants. These remnants could hold all the information about what fell into the black hole. This idea solves the paradox, but raises new questions about what these remnants are and how they work. New physics beyond what we know. Some scientists think the paradox is a sign that we need to discover new laws of physics. These new laws might explain how information is preserved and help us combine quantum mechanics with general relativity. Quantum entanglement and spacetime. A newer idea involves quantum entanglement, which is a mysterious connection between particles. Some theories suggest that black holes might be connected to other parts of the universe through spacetime. This connection could allow information to escape the black hole in unexpected ways. What can we learn from this? The information paradox is more than just a scientific puzzle. It's a reminder of how much we still have to learn about the universe. It shows us that even our best theories might be incomplete. Solving this problem will likely require creative thinking and new discoveries. The paradox also reminds us of the deep connections in physics. To solve it, we need to bring together ideas from quantum mechanics, general relativity, and maybe even areas of science we haven't explored yet. This challenge pushes scientists to think outside the box and question old assumptions. Finally, the paradox raises profound questions about reality. If information can disappear, what does that mean for our understanding of the universe? Can we ever truly know the past, or are some things lost forever? These questions show that physics isn't just about equations. It's also about understanding the nature of existence itself.